you'll have a quiz, standard procedure. It'll be about 9 questions, and it will be about 27 points. I might change one of the questions, so those two things might fluctuate a little bit. It'll be pretty much the same. Now, yesterday's problem with the Bolt Lab, we were like, okay, I don't know the Q or the C. What am I supposed to do with this? And so you take the Q, the water, Q, the Bolt, and you do this whole setup. You do need to know how to do that, just not for this Friday's quiz. So this Friday's quiz, it's gonna be a little gentler. So you're gonna solve for your M's, your Q's, your C's, your delta T's. You're gonna have to be able to solve for all that. And I have a few concept questions for you, like, hey, talk to me about what specific heat capacity actually means, that kind of stuff. But next week, I promise you there'll be a Bolt-like question on the quiz. Okay. So that was a tough calculation, but by then you need to be absolutely cooking on those types of problems. Okay, so just so you know, that is coming down the pipeline. Now, you don't need to write this down here, but today we are going to be going over how to find the temperature of a coffee pot indirectly. So there's a bunch of water in this coffee pot. You will find the temperature of this coffee pot without ever putting a thermometer in there. Okay. We're going to use our Q equals MC delta T. We're going to manipulate some variables. We're going to find a way. In years past, I had people that come up with cups of water. I just pour a random amount of hot water in there. I'm like, go figure it out. And that's all I give you. So this is usually a real thinker question. Similar to yesterday, a lot of people came in yesterday and they're like, okay, I have no idea how to do this Bolt problem. And you've got a little bit of gears turning, and maybe you kind of needed to wait till I went over it as a class to really get going. Some people figure it out on their own. So it'll be a similar thing, where you may not feel like you're doing anything well, because you're going to be very confused. But remember, when you're lifting for any sport or something like that, who's like, oh man, this just feels so good, my arms are going to fall off. No one thinks that feels good, but it's good for you, and it's getting you stronger. In the same way, when you're pretty confused in class and you're trying to figure things out, you're flexing your critical thinking skills, and you are getting better at it. It just doesn't feel great in the moment. Okay, so that same thing is going to happen today. We are going to go over how to do this problem as a class, but you'll probably be struggling a little bit, and that's not a bad place to be. Some things to remember: your Q equals MC delta T, and energy gained equals energy lost. Can't emphasize that enough. You absolutely have to use this concept today, once again, while we're doing the lab. So let's go ahead and turn to the lab page here. One little typo you got fixed in this last box. It says temp H2O. You need to change it to the word mixed temp H2O. So yeah, it's a little typo by old Mr. P. Temp. All right. Now here's what I need. I need a couple people to volunteer to give me a couple of measurements. Barrick, Tanner, come on up. Barrick here, Tanner there.
Yeah, Barrick.
Okay. So I'm going to put a B for his data, T for Tanner's data. First thing I'd like you guys to do, now make sure you zero the scale before you put anything on it. Give me the mass of your empty cups. Go ahead and give me the mass of your empty cups. Yep, those are yours. Yep. Barrick, what are you looking at?
11.72.
Wonderful. Tanner, what are you looking at?
10.55.
Okay. Now, I want you guys to get a random amount of cold water in there. Just don't fill up about more than halfway, but just some amount of cold water. Sure, looks great. You too, Barrick. And get some amount. You can go ahead and zero your scale back out and put it back on there. Looks great. Okay. All right. Now, I'm going to write these next couple of numbers above the chart, okay? I'm going to write these next couple of numbers above the chart here for a second. Barrick, what is the mass of your cup with the cold water?
236.51.
Okay, 236.51. Now, real quick, if I want to know how much cold water he put in here, what do I need to do with this number? Subtract the cups, right? Okay, so go ahead and plug that in for me, folks. Tanner, what was your total?
138.08.
138.08. And we got to subtract his total from that as well. Okay, can someone tell me how much cold water Barrett got? Hey, Terry, you want to move?
I say, yeah, I don't know.
How much cold water did Barrett get?
An amount.
224.79 grams.
224.79. Go and put your thermometer in there for me, would you, Bear? I got yours, Tanner.
Okay.
And how much did Tanner get?
127.53.
127.53. Okay. So I'm gonna erase that. There we go. Alrighty, now. It's over. Now, we're going to tell us what their initial temperatures are of the cold water. Barrick, what's yours?
22.1.
22.1. And Tanner, what'd you get?
It didn't turn on. 21.4.
21.4. Okay. Now, what's going to happen is I'm going to pour a random amount of hot water into their cups. So take the thermometers out for a second. I'll pour a random amount of hot water into your cups. All right, let me just measure this real quickly. Sure. There you go. Yeah. Great. Got some on my shoe. Wonderful. Okay. Go ahead and give me the new temperatures on those. So it may take a second to give me those new temperatures.
It's slowly going up.
Slowly going up. All right, we'll hike those patient pants up for a second. We love our patient pants. Is it? Yeah, maybe you can stir it a little bit with the thermometer too to sort of get everybody mixed together there.
46.7.
Okay, Tanner's got a 46.7. Barracks is still going up.
It's like 40.5.
43.5? Yeah. All right, and will you guys get the mass of, take the thermometers out, but get the mass of the cup and all the water in there? Okay, Barrick, what do you got?
370.32.
Sweet, you are all done. You go back to your seat. And Tanner?
237.89.
237.89. Wonderful. Okay.
Mr. B,
Yes.
wouldn't you have to subtract the cup from the total mass?
Oh, I love what you're thinking. If you want to get the mass of something else, this is just the mass on purpose. This is the total mass. So remember, this is the cup and the hot water and the cold water. Okay?
Alright.
So I see what you're thinking, Muhammad. You're like, wait a second, I'm going to have to manipulate that number. You are correct. Okay? So here's ultimately what you need to do. With just these numbers, you should be able to tell me how hot this water is right here. How hot this water is right here in the coffee pot. Now, some of you may have an idea where we're going. You can go ahead and just get cooking. Some of you may be like, I have no idea what to do next. Like, no clue whatsoever. There are guiding questions right below. So it asks you, okay, what is the mass of the hot water? So see if you can figure out what the mass of the hot water is by itself, and it sort of like kind of gives you direction or where you should be going. So you may not know how to figure out the temperature of this water, but you may be able to figure out the answer to question 1 or 2, and you can sort of get cooking this way. Get some momentum. A couple of tips, okay? Number 1, I would first only focus on Barrick's data because that's our first row. I would ignore Tanner's for now. See if you can figure out with Barrick's, and then use Tanner's as a way to do practice and double check that you do in fact know what you're doing, okay? So I wouldn't be calculating the different numbers for Barrick and Tanner's. I would just focus on Barrick's now because that happens to be the first row we have. I would focus on that. And lastly, really want to emphasize this enough. If you want the Q of cold water, you must use the mass of cold water, the C of cold water, and the delta T of cold water. Okay? So your Q, your M, your C, and your delta T all have to be talking about the same thing. Okay? So if you want Q of cold, you can't be throwing in the mass of hot into that equation, and the delta T of hot, and then the C of cold. Like, it has to be the M of cold, the C of cold, the delta T of cold. So you have to be consistent across the board. Does that make sense? So just be careful with your labeling. I'm going to let people sort of do their thing for a little while. I'll provide some guidance. We'll see how we're doing. We will go over this in a little while, but I want to give you guys a shot on your own, okay? So let's see if we can figure this out, okay? I'm going to go through our breakdown questions. I will need a few people to kind of call out some numbers for me because I can't look at the chart at the same time. So mass of the hot water, let's see here. I'm going to talk about Barrick's data. Can someone tell me what the total mass is cup plus the hot plus the cold, what that whole mass was?
370.32.
370.32. And then we got to subtract a few things. Lexi, what did you take away from that number?
I took the mass of the empty cup away.
Okay, so you took the mass of the empty cup away, and what was that?
The mass of the empty cup was 11.72.
Okay. So hot and cold water in cups minus cups will give you the mass of just the hot and cold water. But I want the mass of just the hot. So what else do I have to take away from this?
The mass of
And what was that?
quick calculator, it was 224.79.
Correct. And what did that mass come out to be?
133.70.
Okay. Again, that's mass of your hot. Okay. I don't need this number right away, but I will need this number soon. So I'm gonna box that up, put it on layaway for a minute here. All right. Next is asking me for the heat energy in joules of cold water. I'm gonna be very careful about my units. Joules. That's asking me for a Q. So I want the Q of the cold. Q is equal to what? What's the equation again? Q is equal to MCAT, MC delta T. So I need to plug in, if I want the Q of the cold, I need the mass of the cold, the C of the cold, the delta T of the cold. Okay? Barrick's cold water had a mass of 224.79. What is the C of cold water? 4.18. Exactly. It's water. It's liquid water, so we're 4.18. Now, what was the delta T? Well, let's see here. His cold water started at 22.1 and it went all the way up to 43.5. So the difference between these two, I think Zach had that on his paper. What's the difference between 22.1 and the 43.5?
21.4.
Yes, sir. Wonderful. So if I want the Q of the cold, I'm going to take the mass of the cold, the C of the cold, the delta T of the cold, and that should tell me what the Q of the cold was. What does that number come out to be, someone?
20107.91.
20107.91? 91? Okay. And that's the Q of your cold, okay? Now, another way to think of this is all the energy that went into the cold water. Bree, where did all the energy that went into the cold water come from? The hot water, right? So the cold water gained as much energy. How much energy did the hot water lose? That same number, okay? So the amount of heat energy that the hot water lost is also going to be this value right here. Okay? So answer 2 and 3 are going to be the same because the Q of the hot and the Q of the cold should be the same. So we started with the Q equals MC delta T of cold. And since that value is equal to the Q of the hot, we can now transition over to hot water calculations. Okay? So that's like the bridge. That's the key step. So then it says use the heat equation to solve for the delta T of the hot. Okay, well, we know the Q of the hot is the same number. So 20107.91. Q is equal to MC delta T. What's the M of the hot? Yep, it's 133. That's not a big deal. It's just a baby rounding thing. Yours is not necessarily wrong. So the mass of that was what we got earlier, 133. Let me see here. Yeah, I think this actually probably should be an 8-1. It shouldn't really matter that much. As I'm looking at it, this should probably be double checking that number 0.81 times. Hey, what's the C of hot water? Still 4. It's still liquid water, right? So it's gonna be 4.18. Doesn't matter the temperature. And the delta T, that is what we do not know. We don't know what that is. Okay? So as I simplify this, I'm going to multiply 133.81 times 4.18 just to kind of clean this up a bit. So pulling out my calculator, 133.81 times 4.18. So to clean this up just a bit, that is 559er.33. What do I need to do to both sides, Mr. Williams, to get this delta T by itself?
Divide the.
Yep. So I got to divide both sides by the 559.33. 559.33. These will cancel out. My delta T will be by itself. What value did we get there? What value did we get here?
I got 35.95.
Okay, so the delta T, 35.95.
Well, it was 9499.
Yeah, so that's fine. Degrees Celsius. So that is the change in temperature of the hot. Is that what I ultimately asked you guys for, though?
No.
No, so you gotta be careful. A lot of people are gonna slap 35.95. They're like, final answer, mic drop. This is the delta T. This will get you a lot of credit, but this is not what I asked you for. I asked you for the temperature of the hot water originally. So, delta T is equal to the initial temp, whatever that was, minus the mixed. So my 35.95 is equal to my initial temp. I'll put INI, because I don't know what that is, minus the mixed temp. What was the mixed temperature?
43.5.
Was it 43.5? Is that right?
Yeah.
I add 43.5 on both sides. This should come out to be 78.
Close to 79.
79.45, it looks like. Is that right?
Yeah.
79.45.
Yeah.
And that must be how hot the coffee pot water is. Let's take a look-see to see if that is indeed the case. So I'm taking the thermometer, plopping it in here.
I said around 80. It's gonna be.
Was that your guess?
No, it was after I had already done it. I'm like, in the pot's gonna make me.
We'll see. 79.0, 79.23. Yeah, pot's about 79.2, 79.3. This is really good. This is solid data right here. Excellent. Okay. Not bad. Not bad. Now, there are 3 things I'm going to suggest you do. You have to do 2 of them, but you can pick the 2. The first thing, you can use Tanner's data to do this same calculation and see if you can do it completely on your own. Now, when you do use Tanner's data, I highly doubt you're going to get exactly 79.45, but it should be pretty close. Upper 70s, low 80s. So if you're plugging this in and, let's say Mooney gets like 4,000 degrees, you're like, okay, I think something's a little off here. When she gets like a 78.5, she'd be like, okay, yeah, I think we're in business here. Okay? So I suggest you either use the Tanner data, or you flip to the next page of your packet and you work on heat equation problems number 2. These are a little simpler. These are good practice for the quiz on Friday, solving for your Q's, your M's, your C's, your delta T's, okay? You do need to be able to do both this type of problem and these, for sure, all right? So you have an option. You can pick between one of those 2 things. The third thing that I'm asking you to do, which is not an option, which everyone has to do, is get those participation points, okay? So take care of those. Now, you virtual folks, the lab that I'm going to do tomorrow in class is the one you guys did last Thursday. So you guys don't need to actually come to live class tomorrow. What I suggest you guys do during this time tomorrow is if you turn one more page, you'll find what's called Calorimetry Practice Quiz A. This guy right here, this will be really good practice for your quiz on Friday. It'll have a similar feel to your quiz on Friday. Be great practice. So there you go. Now, the answer key to heat equation problems number 2 will be in the Wednesday folder. That goes for you live folks too. The Wednesday folder should have the answer key to problems number 2. So virtual folks, get some good practice in. Please email me if you guys have any questions. This is the last time you'll see me live before your quiz on Friday. Okay? So if you guys have any questions, hang out here. But if you don't, virtual folks, you can skedaddle.